You delete a file. You empty the recycle bin. The icon vanishes, but on a hard drive, the contents may still be waiting in space. Windows now calls free. On a modern SSD, a command called trim usually makes recovery impossible. The same click can therefore produce two very different endings. What does Windows actually mean by gone? There is an even faster exit. In PowerShell, Windows text-based control window, the remove item command can bypass the recycle bin. Yet on a hard drive, it still does not scrub the file's contents. Windows releases the file's place in its filing system. The old information may survive until new information is written over it. A new Windows 11 installation already has hundreds of thousands of files, with the count changing by addition and updates. Windows must track each one without pausing your machine. That pressure shaped a crucial shortcut. When you discard something, the system can release its space far faster than it could painstakingly rewrite the contents stored there. After you empty the bin, the familiar routes are sealed. The folder no longer lists the file, search may not find it, and its former address fails. But those are changes to Windows records, not proof that a hard drive's magnetic marks have changed. The screen can confirm that access is gone. It cannot show whether the old contents still survive. Trace your click downward. File Explorer, the window where you browse folders, passes the request to NTFS, the standard filing system used by modern Windows. NTFS controls names, folders, and which storage spaces are occupied, but it does not necessarily order the drive to destroy the contents. First, it changes the records that let Windows find them. Microsoft puts the hard drive rule plainly. Until the space is overwritten, you can recover the deleted data. That sentence exposes the trick. Windows may declare a location available while the previous contents still occupy it. Recovery is possible only during that uncertain interval, before another file claims the space and replaces what was there. Now the story forks beneath your fingertips. A hard drive writes magnetic patterns onto spinning platters, where abandoned contents can linger. An SSD stores information in electronic memory and manages it through hardware you cannot directly control. With trim, supported by Windows since 7, the SSD is told which blocks are unwanted, and recovery usually becomes impossible. Windows does not remember your document as a miniature page tucked inside the drive. It sees numbered storage spaces and a set of records connecting them to a name. To follow deletion, you must step behind the icon and inspect that hidden structure. NTFS has one central list that tells Windows what exists, what it is called, and where to look. Open NTFS's central list, and you meet the master file table, usually shortened to MFT. Every file on that Windows drive gets a record there. Even folders and NTFS's own internal information are treated as files. The MFT is not merely an inventory beside the system, it is part of the system, and it even contains a record for itself. Think of one MFT record as a file's identity card. It can hold the file's names, dates and times, access rules, and directions to its contents. Those stored details are called attributes. Windows can lose the folder entry that led you there, while remnants of this card remain, giving recovery software clues about what vanished and where it once lived. Most MFT records are only 1024 bytes, yet some files need no separate storage area at all. If the contents are roughly 700 bytes or less, NTFS can place them directly inside the record. This is called resident data. The description and the contents share one tiny home. Delete that file, and its recoverable evidence may begin inside the MFT itself. A folder may look like a box containing files, but NTFS stores it as another kind of file. Its contents are an index, a searchable list of names linked to MFT records. Each name can be as long as 255 characters. When you open a folder, Windows follows that list. When a name is removed, your route to the record disappears. NTFS divides a drive into allocation units called clusters, the chunks of space it assigns to files. With the usual 4 kilobyte clusters, Windows supports a file or drive partition up to 16 terabytes. Newer Windows versions can use 2 megabyte clusters, lifting that ceiling to 8 petabytes. The cluster size quietly determines how far the system can grow. The first 16 MFT records are reserved for NTFS itself. Record 0 is $MFT, the table's entry for the table. Record 1, $MFT mirror, protects its critical beginning. Record 2, $log file, helps repair filing records after a crash. Other early entries track the drive, its main folder, free clusters, and startup information. Windows catalogs its own vital organs first. As you add files, the MFT claims more room. NTFS keeps a nearby area called the MFT zone available, so the table can expand without being scattered across the drive. Deleted records can later be assigned to new files, but space already claimed by the MFT is not normally returned. The table can reuse an opening, yet it rarely retreats. When a file is too large to fit inside its MFT record, the record stores data runs, directions to the groups of clusters holding the contents. Those groups need not sit beside one another. NTFS can gather the pieces from different locations and present one seamless file to you. Delete its record, and the drive may still hold every scattered piece. To understand why Windows works this way, rewind past Windows itself. The trail begins in 1977, when personal computer storage meant floppy disks and severe limits. A simple method for tracking occupied space would survive into the IBM PC era. Years later, Windows NT would demand something more powerful, and NTFS would emerge from that break with the past. In 1977, Mark McDonald, working with Bill Gates, created the File Allocation Table, or FAT. It tracked which sections of a floppy disk belonged to each file for Microsoft's standalone disk BASIC 80. Years before MS-DOS, FAT later passed through 86-DOS and reached the IBM PC in August 1981. A small disk solution was about to become a mass-market foundation. Now the ledger leaves the laboratory. In 1980 and 1981, a version called FAT12 appeared in Tim Patterson's 86-DOS, an early operating system Microsoft bought. Then, in August 1981, PC-DOS 1.0 carried it onto the new IBM PC. Bookkeeping built for floppy disks had suddenly inherited a far bigger future than anyone planned. FAT grew with the PC, but eventually struck a wall. FAT32, released with Windows 95 OSR2 in August 1996, cannot hold any single file of 4 gigabytes, the rough size of a feature-length digital movie or larger. As files swelled, that fixed ceiling became a deadline. Microsoft needed a system built for the next generation of storage. That successor was NTFS, the system of rules Windows NT used to organize a disk. Tom Miller and Gary Kimura led a small design team that included Brian Andrew and David Goebel. Miller's original specification ran only about 50 pages, yet those pages described machinery meant to keep Windows organized after crashes and across increasingly large drives. NTFS 1.0 reached customers with Windows NT 3.1 on July 27, 1993. Its disk format became version 3.1 with Windows XP in October 2001 and has stayed there through generations of machines. Microsoft later created REFS, but ordinary Windows PCs still cannot start from it. Even now, NTFS remains the foundation beneath Windows. You can make Windows name the system organizing drive C. Open its text command window with administrator access and run the command shown here. On most modern Windows PCs, the answer is NTFS. File Explorer is only the surface. Beneath every save, rename, and deletion, NTFS decides how the names, records, and storage space must change. The family tree now ends beneath your own keyboard. But history cannot answer the question that matters when your finger reaches delete. Does Windows destroy the file, move it, or merely stop showing it to you? To find out, we must follow one ordinary document beyond the moment its icon disappears and into the hidden machinery underneath. Press delete. The name vanishes from File Explorer, but the contents have not been destroyed. For a file sent to the Recycle.Bin, Windows performs a move on that same drive, placing it under a different name in a hidden folder. What looks like an ending is actually a reversible disguise, and Windows keeps the information needed to undo it. The hiding place is named $Recycle.Bin. Each drive can have one, with separate compartments for different users. Windows labels your compartment with a security identifier, or SID, a long code that uniquely represents your account. This prevents one user's discarded files from simply appearing in another user's bin, while preserving the trail needed for restoration. Windows 2000 and XP used a recycler folder with one info2 index tracking discarded items. Windows Vista replaced that arrangement with the modern $Recycle.Bin layout. Each discarded item becomes a paired entry, and $I file containing its original full path, size, and exact deletion timestamp, and a $R file representing the actual content. The visible disappearance conceals a precise inventory. Ask Windows Text Command Tool to show what File Explorer hides. The commands on screen open $Recycle.Bin and list its concealed contents, if your account is allowed to view them. The names look meaningless at first, but each matching pair shares an identifier. The $I half remembers the file's former life, the $R half carries its contents. Choose Restore, and Windows reads the $I metadata, then moves the $R content back to its recorded path and name. Choose Empty Recycle.Bin, or bypass the bin with Shift+Delete, and NTFS releases the file's allocated clusters. In $Bitmap, the metadata file recording which clusters are occupied or free, the clusters assigned to that file change from allocated to available for reuse. Emptying the bin dismantles the route back. NTFS marks the file's 1024-byte table record as reusable, and removes its name from the folder's list. The file no longer belongs anywhere Windows normally searches. Yet these are changes to the drive's map, not a scrub of the destination itself, the crucial distinction on which recovery depends. Deletion therefore starts a race. On a hard drive, the abandoned locations are now available to any new download, update, or photograph. Until something claims them, recovery software may still follow the leftover record to the old bytes. Once new data lands there, however, parts of the former file can be replaced, and the window begins closing unevenly. Do not carry that hard drive picture blindly onto an SSD. Windows may send it a trim notice saying those locations are no longer needed. The SSD's own cleanup system can then erase them, and recovery is usually impossible in practice. The same click can therefore leave recoverable traces on one kind of drive and rapidly destroy them on another. Now, imagine the power failing halfway through a save. Windows may have changed a file name but not the record showing which storage spaces belong to it, or updated those in the opposite order. The drive's own lists could disagree. Yet NTFS is built to recover a consistent structure after many such crashes. Its safeguard is a journal written before the risky changes begin. NTFS is a journaling file system. Before changing its own structures, it records enough information to complete or reverse the bookkeeping. That record lives in $log file, the transaction journal stored as record 2. Its redo information describes how to finish a metadata operation. Its undo information describes how to back it out. The diary entry comes first. Only then does NTFS perform the change. The journal's promise has a hard boundary. It protects NTFS's map, names, indexes, and records of used space, not the words or pixels you were writing. After a crash, Windows can restore an orderly file system, while the latest contents of your document are still missing. The shelves may be straight again. That does not guarantee the unfinished page survived. Windows exposes 2 clues from this hidden maintenance layer. One command asks whether the drive is marked dirty, meaning Windows suspects its bookkeeping needs inspection. Another reports a separate running record of changes, which we will examine next. Neither command retrieves your document. They show something more fundamental. NTFS continuously checks and records the condition of its own map. When Windows reconnects the drive after a crash, NTFS opens $log file, its record of unfinished bookkeeping. It can complete changes that had begun or reverse those left halfway. You may not recover the very latest moment. What you gain is more fundamental. The drive's lists, names, and map of occupied space no longer contradict one another. But open the rescued document, and there may still be a wound. The final paragraph missing, an older draft restored, or a save cut in half. $log file repairs NTFS's filing system. It does not create information that never finished reaching the drive. Windows can restore an orderly cabinet while the page inside remains damaged. Now meet a file with more than one front door. NTFS calls each extra name a hard link, a different folder entry that opens the very same stored file rather than a duplicate. One file can have as many as 1,023 such names. Change it through one door, and the change appears through all of them. Windows uses this trick in WinSXS, the store that holds important system components. Files shown in other folders may simply be additional names for content already there, so a counting tool can mistakenly charge the same material more than once. Delete one name, and the file survives through the others. Its space becomes free only after the last name disappears. Suppose the missing file is precious. Recovery software does not search for a hidden safety copy. On a hard drive, it looks for an abandoned MFT entry, the old card that may still reveal the file's name and former location. If neither that entry nor those locations has been reused, the vanished file may still be pieced back together. An undelete program reads MFT entries that NTFS has marked available, then follows their old directions and saves whatever it finds somewhere safe. The result may be complete, damaged, or empty. Later activity can reuse the entry, the file's former storage spaces, or both. Even opening programs can reduce your chances because ordinary work creates new data. Microsoft offers its own rescue tool, Windows File Recovery, also called WinFR. Released free in summer 2020, it works on Windows 10 version 2004 and later through typed commands. You might search Drive C for lost Word documents and send the results to Drive E. The drives must differ, so the rescue attempt does not overwrite what it is trying to save. Format sounds final, but the option and the era change everything. A quick format does not overwrite old contents. Before Windows Vista, even a full format mainly checked the disk's storage areas and left existing bytes behind. Since Vista, a full format writes zeros across the entire selected section of the drive, a far more destructive act, hiding behind the same button. Now, the recovery window enters a criminal investigation. In February 2005, the BTK killer sent a purple Memorex floppy disk to Wichita television station KSAS-TV. The medium looked disposable. Its deleted contents were not. Before the month ended, a digital trace from that disk would help turn a decades-long unidentified killer into a named suspect under arrest. Examiners recovered a deleted Microsoft Word document from the floppy itself. They were not guessing from nearby clues or opening a secret backup. Enough of the discarded file remained to read. It also carried metadata, information stored about the document rather than printed on its page. That invisible information pointed beyond the writing to the person who had saved it. The hidden details named the last user as Dennis and mentioned Christ Lutheran Church. Investigators connected both clues to the church council president, Dennis Rader. Familial DNA then confirmed the identification. The chain was brutally ordinary. A deleted document survived, its stored details narrowed the search, and separate biological testing established that the man was BTK. Rader later reduced the entire failure to 6 words. The floppy did me in. He had trusted the disappearance on screen. Investigators trusted what the disk still held. That gap between what a computer shows you and what its storage retains helped end one of America's longest-running murder investigations. Deletion had hidden the document from him, not from the examiners. Now step inside an SSD, where the recovery window can close without another file visibly taking its place. Unlike a hard drive, an SSD stores information in flash chips and contains its own controller, a tiny manager deciding where data goes. Windows asks for numbered locations, but the controller chooses the actual cells and may erase abandoned information in the background. Flash memory has an awkward rule. Before part of it can be written again, a larger region may first need to be erased. So the SSD's controller often writes new information elsewhere, carries forward anything still needed, and later clears space in larger batches. Your deleted file can therefore enter an unseen disposal process controlled inside the drive, beyond the recycle bin. Flash cells wear with repeated use, so the SSD spreads writing around, a practice called wear leveling. The numbered locations Windows sees are only a convenient map. The controller connects them to changing physical spots inside the chips. An older copy may linger for a short time, but Windows cannot address that hidden spot directly, and the controller may soon erase it. The turning point arrived with trim, an ATA storage command. Trim lets Windows tell an SSD these numbered areas are no longer needed. Windows 7 became the first Windows version to support it in October 2009, shortly after Linux. From then on, deleting a file could trigger more than changed bookkeeping. It could authorize the drive itself to begin destroying the discarded contents. Trim does not send the SSD your file name or folder. It sends ranges of numbered storage locations that Windows no longer needs. The controller may then stop carrying those contents forward as it rearranges the flash, allowing background cleanup to erase them. This is the crucial handoff. Windows releases its claim, and the SSD gains permission to dispose of the underlying data. You can ask Windows whether this handoff is active. One typed command reports whether delete notifications. The messages that include trim are disabled. For NTFS, 0 means they are enabled. Another command can request retrim, sending the list of abandoned areas again for drive C. Retrim does not overwrite them itself. The SSD decides how and when to clear them. Inside the SSD, a tiny manager is quietly cleaning house. It gathers data still worth keeping, moves it elsewhere, and clears a larger patch of memory for reuse. A trim message tells it which pieces may be abandoned. Many drives then show those locations to Windows as empty almost at once, although the actual clearing may happen later. Here is the consequence. On an SSD, a deleted file can pass beyond practical recovery while the machine sits apparently idle. Once the drive has processed Windows' trim message and cleared the unwanted memory, recovery is usually impossible. Not always. The result depends on that drive's built-in instructions and timing, but the old hard drive rescue window may slam shut by itself. You are about to sell a laptop. Not hide its files, not abandon their addresses. Make the old bytes unreadable, even to the next owner. Windows offers two radically different answers: overwrite the discarded space, or destroy the secret that makes the entire drive intelligible. One touches the storage repeatedly. The other barely touches it at all. Windows includes a command called cipher/w for wiping space left available by deleted files. It fills that reusable space in 3 stages, first with zeros, then ones, then random data. Your files that still exist are left alone. Built into Windows since XP, the command targets the leftovers deletion did not physically remove from a hard drive. 3 passes may sound reassuring, but modern guidance says 1 overwrite is enough for today's drives. The celebrated Gutman method demanded 35 because it was designed around ways that 1990s disks recorded information. On current hardware, piling on extra passes mostly piles on waiting time. More motion does not automatically mean more protection. The obsession with repeated wiping did not go unchallenged. Peter Gutman later said his elaborate method was unnecessary for modern disks. In 2001, Microsoft added free space wiping to the cipher command. 5 years later, a public challenge invited experts to recover information after a single overwrite. The prize-winning recovery never came. Nobody claimed the challenge. On screen, type cipher W followed by the location on the drive you want treated. That location identifies the drive. Windows then wipes all reusable space there, not merely the named folder. Remove the unwanted files first, because anything Windows still recognizes as a current file is protected from the wipe. On a roomy hard drive, prepare to wait. There is a trap. Cipher/W cannot see an SSD's hidden past. Windows requests writes to numbered locations, but the SSD secretly chooses which memory cells receive them, and may have moved earlier copies elsewhere. Chasing every remnant is therefore unreliable. The stronger modern strategy is to encrypt the drive, then destroy the key that makes its scrambled contents readable. BitLocker is Windows' drive encryption system. It turns stored information into an unreadable scramble that only the correct digital key can unlock. Windows 11 version 24H2 normally switches on device encryption for a new installation, including Home Edition. When you sign in with a Microsoft account, reset this PC destroys the old key, making the remaining encrypted information unreadable immediately. Before handing over a laptop, check that device encryption is on. Then use Reset This PC to destroy the old key. For a hard drive that was not encrypted, wiping its reusable space remains an option. What matters is not whether an icon has vanished, but whether anything left behind can still reveal your files to someone else.